and all. On behalf of the organizing committee,
A very good morning. Dr. Sonia Parsekar, Assistant Professor,
take this
take this
privilege
privilege to welcome
all
all
the
the
dignitaries,
dignitaries,
resource
resource
persons,
persons,
faculties,
faculties,
research
research
scholars,
scholars,
students,
students,
and
and
others
others
for
for
today's
today's
national
national
webinar
webinar
on
on
emerging
emerging
trends
trends
in
in
heavy
heavy
metal
metal
detection
detection
sensors and
sensors
CH
and CH
functionalization,
functionalization,
organized
organized
by
by
Department of
Department of Chemistry, Dhempe Charities Trust, Dhempe College.
I request our Madam Principal, Professor Brinda Walker, to give
Of
introductory
remarks.
Good morning. Good morning and welcome to the national webinar on emerging trends in heavy metals detection sensors and CH functionalization, organized by Department of Chemistry of our college. I take pleasure in welcoming all the participants, teachers, as well as Dr. Hazra for this webinar. Welcome, sir, to this webinar. Is celebrating its 60 years of establishment. It was established uh, 62. This college was established. So within 6 months it was, and so we are celebrating 60 years of our establishment. On this occasion, we are trying to this thing, remember the founders by organizing various webinars because it was pandemic, and of course now we are also started with seminars and offline workshops. But we felt that that is the correct tribute to our founders, and I'm very happy that Department of Chemistry has already organized one international conference, and now this is a national conference that they are organizing during this year. I appreciate the efforts taken by the head of department, Varsha Virjinkar, and her team for organizing this welcoming. Student Hazra will who have joined, participants who have joined this webinar will be benefited by his experience as well as today's talk. Thank you, sir, very much for joining and being with us. We would have been definitely happy to host you in person in Goa because we always enjoy people coming to the campus and interacting with the students. However, because of pandemic, this new window is given to us of webinars, and we are making best use of it. So, welcome again, all the participants as well as Dr. Hazra. Thanks.
will be delivered by
Thank you,
Professor
madam.
Hazra. Title of
Today's
this
national
lecture
webinar
is Small Molecule-Based Sensors for Detection of Heavy
includes
Metals.
2 lectures.
It gives me great
First lecture will be delivered by Dr. Subhanjit Hazra. Title of his lecture
post
is
of scientists
It
see
gives me
at the
great
Center
pleasure
for
to introduce Dr. Subhanjit Hazra. Center for
of
Nanoscience
Science
and
and Technology,
Nanotechnology, Satyabama
Satyabama
Institute of Science and
completed
Technology,
his
Chennai.
BSc in
Dr.
Chemistry
Subhanjit
from the
Hazra
University
completed
of
his BSc
Udvan,
in Chemistry
India
from the
in
University of
2007.
Udvan, India
He
in
completed his MSc
2007.
in Organic
He
Chemistry
completed his
from
MSc in
Assam
Organic
University.
Chemistry from Assam University, Silchar, India in
Was
2009.
awarded PhD
He was
degree
awarded
from Birla
PhD
Institute of
degree from
Technology
Birla Institute
and
of
Science.
Technology and Science, Pilani in
He also
2015.
worked as a
He
research
also worked
associate
as a
at
research
IIT
associate at IIT Guwahati, India. He is also a
D.S.
recipient
Kothari
of Dr. D.S.
Postdoctoral
Kothari
Fellowship, UGC
Postdoctoral
India.
Fellowship,
He
UGC,
carried
India.
out collaborative research
He carried out collaborative research with
microwave absorbing materials
Defense
and Professor Paul K. Linda,
Laboratory,
University of Leeds, UK, on fluorescence-based materials and sensors. He has
on
29 publications
microwave
in his
absorbing
credit.
materials
His
and with
research interest
Professor Paul
includes
based
synthesis and
materials and sensors.
characterization of nanomaterials
His
and their
research
surface
interests include
functionalization,
synthesis and
nanocomposites,
characterization,
synthesis of heterocyclic
nanocomposites,
compounds,
synthesis of
organic
heterocyclic
synthesis,
compounds,
heterogeneous organic compounds-based chemical sensor,
organic
lithofluorescence
synthesis, heterogeneous catalyst materials, electrochemical sensor, biosensors, synthesis of polymers and composites.
introduction. I
With Hazra to take over the session.
Thank you, ma'am. Thank you very much. Am I audible? Hello. Am I audible, ma'am?
Yes, sir. You are audible.
Okay.
You are
Okay.
audible,
Thank you,
sir.
ma'am. Thanks for your kind introduction and inviting me for this webinar. So I would like to thank Principal Ma'am and the organizers, and particularly my senior, Dr.
Yes, sir,
Bhanudas
you are audible.
particularly Dr. Bhanudas Naik, who is a faculty of your institute. Because we did a PhD from the same lab, and it's like almost 12 years of like we know each other. So thanks to each and everyone who like taught me that I can give a lecture for this. And basically now I'm working as a scientist. I'm assistant professor for in the Department of Chemistry and Center for Nanoscience and Nanotechnology in Satyabama Institute of Science and Technology. Now, shall I start my presentation?
Yes, sir, you can start.
Yes. My slide is visible to you? Ma'am, is my slide visible?
Yes, it is visible, sir. It is visible.
Okay, so now I'll start and I'll try to finish by minutes this my lecture. And uh, my topic is that small molecule-based sensor for detection of heavy metals. So now, what is sensor? The sensor is a device that measures physical quantities and converts the signals which can be detected and analyzed. So if we see the applications, it has selected now each and everywhere you can see the sensor devices, like in defense, for environmental applications, for healthcare, biomedical. Even now, I think each and every family they know about that the test kit of that blood sugar test kit, so which is also that one of the biosensors, which is like now world is using maximum uses of that because cheap-based device for our sensors, what it can do, it can save the time, it can save the cost. And everything. So now that's why the development of sensor is a huge research area, and now people are fully focused on that to do the development of new sensors. Okay. So how sensor work? So if you are having an analyte which will First, you have to make the for the sample preparation. Then you just put a drop or like blood drop or something. So it's for the sampler. Then there is an array of sensors which can basically bind with this analyte, and then they will produce some signal or some data. Might be chemical. It might be electrochemical. It might be like some color or something it will generate. Then you will have some algorithm where the pattern will recognize, okay, so this much of color or this much of voltage or this much of your current means that means it's the analyte concentration. So there will be linear regression where that you will have a calibration curve. As per the calibration curve, you get the pattern. Suppose if you're like looking for some environment toxicity, so is it like really toxic or not? That will come to know. So now
For the interruption.
this is basically what I told that this is a sensor. The three sensors should be selected.
Sir, excuse me, sir. So sorry for the interruption.
Sir, please share your presentation in slideshow
Sir,
mode.
sir, please share
Hello.
your presentation in slideshow mode.
It's already slide so mode, ma'am. Okay, I'll try to do it. Now it's okay. Hello. Okay, I'll just stop and again.
Okay, sir. Okay, sir. Thank you, sir.
Now it, okay, just a minute.
It is not visible. Presentation is not visible. So please share it.
So now it is not visible. Presentation is not visible.
Yeah, yes, ma'am. Yeah.
So please share it again.
Yes.
फुल स्क्रीन करू शकतो मिस्टर स्क्रीन शॉट केलं साइड शॉट करू काय नाही घेत प्रॉब्लेम आहे गुगल ॲप तरी
Now it's visible, ma'am.
आता आले ओके ओके यस यस
Is it visible, ma'am? Now.
It is visible, sir.
Now is it full screen or?
यस
No, it is not full screen.
No, it is not full screen.
On below, sir.
There is one icon below, sir. Please click on it for the slideshow.
Yeah, I'm clicking on that actually, ma'am. But here I can see the full screen. So might be. Now is it full screen, ma'am? Because here it is showing full screen actually.
Sir, it's okay, sir. Please continue.
Okay, so different types of sensor. If we talk about,
I know,
there are
yeah.
like chemical sensors which can change the chemical composition.
आता स्लाइड चेंज आहे ना गुगल शेअर करताना शेअर फुल स्क्रीन किती केलेलं आहे स्लाइड मोड आहे ना
Then there is like biosensor
स्लाइड हे करपाचे
that
स्लाइड
depend upon the enzyme
विंडो
interaction,
करपाचे
the
प्रेझेंट
chemical
विंडो
विंडो
फुल
करपाचे
स्क्रीन
and
उसने केलं तुम्ही किती मिनिमम
another
सगळं
thing like some physical
विंडो करपाचे
something like pressure
विंडो में पिपडे
sensor
सिलेक्ट करपाचे
and mass like
विंडो
in the mass and the pressure we can change and
जसं
optical also we can do like
स्लाइड चेंज
proximity and light.
जर केला तरी तर
So all these
त्यानंतर त्याच्या ह्याच्यावर केला असतील
we are having some changes is there.
केला असतील असं डान्स पण केला असतील बरं
You
आपल्या
get some
ह्याच्यात
signal and you can feel the
चेंज झालं तुला साठी पाहून होतं
So this is like in our body. So our tongue is actually have full of the taste buds. So which are basically all small sensors. So when we are eating something, so that taste actually is now transmitted to our brain, and we are saying, okay, this is taste is good, or this taste is bad, or something, or whatever we are eating, we can tell, okay, this is a sweet or this is salty or something. Okay, so there is like sample analyte. This is the immobilized receptors. These are the transducer part, and then particularly it is that we are like saying, okay, physically it is like not recording our brain, okay, that we are getting this taste. So there is like sample analyte. This is the immobilized receptors. These are the transducer part, and then particularly it is that we are like saying, okay, physically it is like narrating our brain, okay, that we are getting this taste. So So, like kind of example, like biosensor, if we
So,
talk about, so
excuse me,
there,
sir.
what is
So,
the
excuse me,
what?
sir, for interrupting again.
Yes, yes, ma'am.
Sir,
Slide is
your only first slide
visible,
is
sir.
visible, sir.
Oh, is it? Okay.
Now it is changed.
Yes, sir.
Now we could
Now we could see, sir.
Now it is like full screen, ma'am.
yes, sir. It is okay.
Ma'am, this full
Now the
screen.
Please continue, sir. Yeah, it is.
हम्म.
Yes, please continue, sir.
त्याका दिसत असतले त्याच्या लॅपटॉपाचे ना तो स्लायडिंग आपल्या येतं
yes,
ना
please
Visible,
continue,
ma'am.
sir.
शेअर पण
Okay. So there, I think
Yes, it is visible.
yeah. Now it's full screen or ma'am? It's like in.
प्रॉब्लेम शेअर
It is
टॅप
not
करो
full screen, sir.
शेअर विंडो
It
करो
is
ती
not full
विंडो की
screen, sir.
नाही स्क्रीन तू ओपन करून तुम्ही स्विच कर विंडो अरे मी त्यांची अपडेट झालं सगळी अपडेट करीत असा अपडेट
Now it's visible, ma'am.
Yes.
Yes, sir. Visible.
Yes, sir, visible.
It is visible, sir, but not full screen.
But actually, I am getting a
Yes,
full
and
screen.
असे
Okay,
विषय
let it be, sir, but it is visible. That's okay.
Okay. Okay, okay, ma'am. Thank you. So, like for biosensors, like you can see the bioreceptor, the different bioreceptor, like enzyme, like antibody, nucleic acid, these kind of things will be immobilized to the receptor. Then the transducer will be like optical, electrochemical, or piezoelectric. Then it will be amplified to the digital signal. So, it is basically the workflow for any sensors. So, like I given this example because of like biosensors. Now people are all are working on biosensors and all this, which is a very known terms to everybody. So what kind of analytes we can check like pathogens, heavy metal, pesticides, and explosive everything. Anything we can like check. And what are the receptors like antibody, enzyme, and aftermarket. So antibody and enzyme those are bigger molecules compared to the aftermarket are a small molecule. That is, yeah, as my topic is small molecules, so today I will just give one example for the aftermarket sensing also. So then what are the transducers? Transducer like different nanoparticles people are using like graphene, carbon nanotube, or RGU kind of things, or even metal nanoparticles also people are using for the transducer. Then now response we are getting like if it is electrochemical, then we get like current, potential, or resistor. Any change you can see, you can say okay, this change will come definitely because of the interaction of the analyte with your receptor. So then only we will say it's a sensor. So to make a sensor, so there is like very famous is that lock and key theory. So it should specifically bind to the receptor site your analyte. Then only it will show the signal. Otherwise, it will not give any signal, and your sensor will be not selective or not specific to the particular analyte. So specificity and selectivity should be very important criteria for any sensors. So now I come to slowly to my topic about the heavy metals. So we all know the mercury that we are like it's the one of the most toxic heavy metals. So there is a cartoon that one tuna actually the fish is now saying that I am free of dolphin, but I am full with the nickel mercury because that heavy metals in marine environment is like, particularly the mercury because of the reason behind that is all the industrial waste and everything directly basically polluting the water. So what are the heavy metals? Heavy metals like the metallic element which are the denser than the common metals like mercury, lead, cadmium. So if you see the light metals like aluminum, magnesium and all, so they are having 2.7 or 1.7 a heavy metal. So why they are so toxic? Because extensive use of heavy metals in the industries, like even that leaded petrol. To gain the better performance, people are using lead adding to the petrol. So leaded petrol, so that lead basically coming out to the environment as a pollutant, and we are basically polluting the environment. Even for that industry like dye stuff and everywhere people are using in this mercury and CFL bulb that for bulb industries and all they are extensively using the mercury vapors. So then these are highly toxic and these are widely distributed. Actually, there is so like in our art first there is so much of heavy metals present,
So sorry, sir.
and the ultimate
You are still on the
yeah.
Sir,
slide six.
you are still
Slide
on
six
the
only
slide
visible
6.
to
Slide
us.
6 only is visible to us.
Even I'll try to share my.
Yes, yes. Now, still I can see.
Now it's visible, ma'am.
You
Now
can
we
see.
can see slide two.
Now we can see slide 2.
Slide 2 or 3.
2.
Now it's changing or it's not changing, ma'am.
We can see slide 2.
Okay. Can you give me just 1 minute? I will call one.
Window share करती go ahead. इसका मतलब लगना है.
Participants kindly bear for the technical difficulties. We'll be back soon.
तुझे करे मिल जाता है. तो स्क्रीन शेअर करता मरे आणि स्विच कर ना पीपीटी स्विच जायना तो एंटायर आता त्याने एंटायर स्क्रीन शेअर केले तेका एंटायर स्क्रीन शेअर करपाचो आता केले एंटायर स्क्रीन शेअर करता आणि पण तो जण जोडलो सो तुला लूप जाता त्याची इमेज परत एंटायर स्क्रीन केले ना आता पण तो स्विच जावना पीपीटी कसो हा तेका ती स्क्रीन दवरली जाल्यार म्हणजे गुगल मिटाची सो तीच मागीर
एंटायर स्क्रीन करता
आता परत केला जाल्यार परत करता आता स्विच करपाक जाय जस्ट स्विच करपाक आता डायरेक्ट पीपीटी मारल्यार
पीपीटीन वचूंक
आता एंटायर स्क्रीन शेअर जाता
सो आता कॉल कर आताच करायचं आणि त्याला डायरेक्ट आता पीपीटीन स्टॉप करनाका सांग डायरेक्ट
केले पण तो म्हाका परत त्या विंडोन वचूंक वयता गुगल मिटाची
तेका सांग तशें डायरेक्ट आता स्क्रीन शेअर
हेच करता पळयता परत कॉल कर तेका सांग गुगल मिटा विंडोन वचनाका सांग स्क्रीन ऑलरेडी शेअर करता सांग फक्त
कॉल कर
पीपीटी ओपन कर म्हाका दिसता सांग तो परत गुगल मिटार वयता स्क्रीन शेअर करता आनी गुगल मिटार वयता आता परत तो थंय वता तेका
आता डायरेक्ट प्रेझेंटेशनान गेलो
आता सारकें
मी नाव विजिबल म्हणून सांग
नाव विजिबल
नाव बिटी विजिबल
आता विजिबल
झाले झाले
केल्ले ना परत हे करता तू येता आता परत डिस्कनेक्ट हे करता
ते कॉल कर सांगू
परत येता पळय आता
नाव मेक इट फुल स्क्रीन सांग
So please make it full screen.
नाव विजिबल
Yes, sir. Now it is clear.
Yes, sir. Now it is clearly visible.
Now,
Please proceed,
now
sir.
changing.
yes
Now
yes
it's changing.
Yeah, now it's changing.
Okay, thank you. Sorry, sorry.
Thank you, sir. Thank you, sir.
Okay, so then I think uh, so I was here about I was speaking about the heavy metals. So then, like if any metals which is dense than the common metals, so we'll tell them as we'll name them as heavy metals. So like mercury, cadmium, lead, copper, and all. So now, toxicity of heavy metal, why it is happening? Because the inhalation of the mercury vapor is a like for metallic mercury, and it is dangerous because it's like for cation, if it's ionic compounds, then it will be definitely soluble, and if it is organometallic, then it will directly bind to the organic molecules. So basically, as you know, that heavy metals are basically a soft acidic parts, so it has high tendency to bind with the thiol group, which is present in the enzyme in our body. So it will directly go. So suppose you are taking any food stuff which is having suppose this mercury or lead or cadmium. So it will directly bind to your enzyme, and then it will be like accumulated to your body, and you will get the toxicity. So like here I given this heavy metals. So what are the things can happen? It can be like enzyme inhibitions. So after generation of reactive oxygen species, and then it will imbalance the antioxidant level of our body. Then it is having very high affinity to bind with the sulfur content biomolecules, because sulfur is a soft thiols are all that is a soft center. So as per the Hubs of acid base concept, so it will bind with the soft base, and it will become it will make a huge complex, and then we are basically getting the neurotoxicity or nephrotoxicity things that will happen. So then other things what can happen is suddenly have the oxidative stress like cell apoptosis and like cell death will happen, and it can even inhibit the DNA mismatch repair, so that will cause the cancer. So these are the different toxic heavy metals, and if we can see that maximum of the heavy metals, either they are having that they are attacking either the nervous system or GI tract. So then, and all are having basically uh, they are producing oxidative stress, and they are giving like ROS loss reactive oxygen species emission, and ultimately that killing the cells, and basically we are getting uh, different kind of diseases like some liver problem, kidney problem, lungs problem, and all these things. And ultimately, cancer is also one of the biggest reason where the mercury that rheumatology is one of the biggest reason for the cancer also. So now these are the permissible limit by the World Health Organization Control Board and ICM are our Indian Council for Medical Research. Potency mechanism. One is that the mercury and one is the copper. So you know the WHO limits like for copper 1.3 and this 0.001 milligram per liter. So that sources like combustion of coal, then solid used to solid waste, then the mercury you are getting, and copper we are getting in the fertilizer, automatic cell, and already I discussed about the side effects. So it is having huge health effect. So uh, now about mercury, mercury is like can form amalgam with maximum number of metals. It forms many metals like gold, silver, tin. It can form the amalgam. These all are used for the application for industrial applications, different kind of industrial application we are using this, and and one more thing is it's liquid in nature in ordinary temperature. So that vapor from liquid to the vapor is formed. So then it will be like that we can inhale in our body and direct oxygen can happen. So so how it will bind? So mainly the methyl mercury, like organometallic mercury, and mercury nitrate or mercury chloride. These are the compounds which are basically more toxic in nature, and it can be like enter your body, even it can enter through your body through the skin. If that's why when we are working with mercury swords, so we should be very much careful that it should not touch to your skin. If it touch to your skin also, then it can easily enter to your body and it can be like very much harmful to the body. So these are the different effect for this exposure. If it exposed, then what are the things? So ultimately, anything can happen till death. Like it can even cause the death. So that's why uh, we have to be very much careful. Like organomercury effect, like methyl mercury. So exposure in the even if one like mother can consume the fish or something which having a methyl mercury, so it can be transferred to the fetus, that baby, and even baby's brain and nervous system, and that can be affected by the heavy metals, like particularly mercury. So there are some and I can say famous. It's like infamous, like some diseases like Hunter Russell syndrome. So how it happens? This is because of the mercury poisoning. I'm the worker in the factory of Norwich. So they all actually breathe methyl mercury. And they got this Hunter Russell syndrome, which is a neurodegenerative disorder, and then. The famous Minamata disease in Japan. So that also almost 600 people died, uh, and this is also because of the contaminated fish that by mercury, because all the industrial effluents that come to the sea water and it was taken, and it happens. Then what? Then in Iraq 1971 to 72, so there are 459 people died because of the methyl mercury based the fungicides it caused. Even see now, as we are doing all research and all, so now in 1996, this lady, this Karen Wilterham, lecturer from Dartmouth College, chemistry professor, was still a small amount of dimethyl mercury, and she exposed to the mercury, even giving the GSM therapy, like they have, because for this uh, they are using basically therapy like different genetic metal like EDTA or some reason which will basically bind the metal ion, and it can be taken out from your body. But after all this also she died after a few months because of the mercury toxicity. So now I will come to my work. I show some of my work like I did for marketing. So this is the recent work, not even recent. It's almost 2 years that we did during my postdoc. So this is a novel tryptamine appended rhodamin based turn-on chemosensor for the detection of Ag2 plus in aqueous media. And this article was published in Analytical and Bioanalytical Chemistry, and it came as a cover image of the that particular issue. So why we need rhodamin-based chemosensors? Because as I told already that it's 10 nanomolar is the as per US EPA this contaminant level of the Ag2 plus. So we have to detect Mercury 2 plus below these 2 ppb that your threshold limit. So there are several techniques are there like atomic absorption spectroscopy, AES, XRF, and all this stuff. But for this detection of heavy metal, but the problem is that they need particular your processing of the analyte, you need trained manpower, and the cost of the instrument are very high, and maintenance also cost. And another thing is that if you want to do in like real life application, like in field, so then we need something. So you can't take an X-ray for any one VAs to the field and you can do it. So for that we need something which can be like easily can diagnose this analyte and which can show some sensing property, like changing some properties and that. So why we took that chromogenic like probe, because it can be detected in the bare eye, you can detect it. So if color change, definitely we can say okay, there is some change in color, so it might be this because of the binding of the analyte. So even now this actually rhodamin based also this fluorescence signal, because this is the rhodamin and fluorescent kind of dyes, they are having high quantum heat and high absorption coefficient. So it can be easy like if it binds, so immediately we will get some color or some fluorescence. So then we can easily we can say okay, this is a good sensor. And but you have to keep in mind that it should be highly selective, sensitive. Response time should be short. Like we can't wait for a like day to response for a sensor. It may happen that some sensor can respond after 1 hour or 2 hours. That is for practical application point of view. So it will be it is not good to have something so which will take much time. And here, like there is no much sampling. Like you just take your solution, you put your quantum into water, and you can get that color. And when you take tryptamine, because tryptamine is a amino acid, like it's analogous to the amino acid tryptophan, and it is almost present in all the neurotransmitters. So which so it is also because you have to keep in mind your sensor should be highly biocompatible. So if you can modify your rhodamin moiety or fluorescent moiety or whatever any dye molecule with your having something which is more like non-toxic in nature, so then it will be more biocompatible to your for your particular application. Now this is the synthesis step. So first we took the rhodamin dye, then we in case of PC solvent, so we reacted with POCl3 to make a COCl, and then we add tryptamine and triethylamine. So after that we got this intermediate with purified through the column chromatography, and then then this moiety actually was selectively like recognize the trivalent patterns like chromium 3 plus, iron 3 plus, and aluminum 3 plus. But when we made it to double bondage using lossless reagent, we made double bond O to double bondage. Then it was specific to the material, which is quite obvious because double bondage means it will be particularly specific to the heavy metals like which is the soft acidity. So now we characterize using the Proton Nmr. So I'm not doing details of that, and 13C Nmr. So you can see this pyrocarbon around 73. So this that means this thing happened, and we can see the mass of this 601.3073, which is exactly matching with the theoretical mass. So it's like m plus h mass which is matching. So we can say our compound form. And from IR also you can see this NH stretching and as well as that C double bond is stretching at 11:15. So this also confirm this formation of the C double bond is bond. So now it comes to the sensing study. So when sensing study, first we have to check about the solvent. So what solvent will be suitable? So then we checked with acetonitrile, PHF, DMSO and methanol. So then we find that methanol having the maximum intensity. So because as per the polarity and your compound your sensor structure it depends. So after getting the methanol as the highest intensity, so then we try if it is in methanol. So now detecting in water will be problem. So what we did then we vary the water and methanol concentration and we see that 70% of methanol, 30% of water. So then there we got the maximum number of fluorescent. So that means that our compound is, if your analyte present in water also, so as the mixture of water and methanol, so it can be used as a, we can say this can be detected in the water medium. So we check for different pH. So pH stability we should check for any like if it is applicable for wide range of pH, it is stable. So then we can say okay, this compound is highly. So you can see for pH 6 to 10. So there is no much similar indices. So when it is the black one is basically your our sensor. So when I add the mercury, so immediately the intensity changes. But from pH almost I can say 5 to 10 it's fairly stable. There is no much variation in the thing. So that means from pH range 5 to 10, your any pH range it will be applicable. But if it is more acidic, so then it is showing some intensity because as the structure, you can know the structure from this. So when it will be in acidic structure, so I go when it's acidic structure, so this bond will again start opening. So then we'll get the fluorescence intensity. So and I told that response time also we have to check. So we check the response time and you can see within 4 minutes of time we are getting the that signal like fluorescence intensity as well as the color intensity we are getting. So and you can see after 4 minutes, whatever you are in the doesn't change much. So you can say that 4 minutes, in the 4 minutes our sensor will work. So this is the titration for like, to 10 micromolar of the sensor and then if you want increasing mercury here, so you can see the fluorescence intensity and this is the absorbance sector, so you can see the also absorbance also increasing.
सर्टिफिकेट
So now for the selective selectivity test, what we did,
चला
so we
डायरेक्ट बजे
checked
डायरेक्ट
from like
सर्टिफाइड डायरेक्ट
sodium,
पहले
potassium,
पता रास्ता
aluminum,
में
barium, calcium,
तो
iron, magnesium, salt, like 7 metal ions, and then we added here. But you see there is no much difference with the probe, like our sensor. But when you put the mercury gas, then it is very high. So what we did, we put mercury against all the metal ions. They are also getting. So if your interfering metal ions also present there, other metals are present there, in everywhere it is so only if it is of the Ag2 plus, then only it is sodium. So that's good for the absorbance also. So now you can see the color change. So you can see that color, like green color is formed and orange fluorescence also formed only in case of mercury. Okay, but when there are little bit color from for silver and because that all because of the soft hard surface interaction. But the interaction with the mercury was highest, so that's why in mercury we got the color as well as the fluorescence. So now with the sensing part, now we have to draw the mechanism. So for that, what we did, this is the famous Jobs plot. So why do we change the mole fraction of the mercury, and then when how do you check mercury and your sensor? So what is saying that 0.5 x equal 0.5, that means 1:1 binding is happening. So that means one sensor molecule is actually sensing the binding with the one of the Ag2 plus. And binding constant also we calculate, and it was 10 to the power minus 10 to the power 5 range, which is fairly
Hi.
high. Hello, hello. Okay, so which was fairly high, so that means it's binding very strongly, you can say. Now, you can see when we did the mass spectra of your mercury plus this probe, and we got one peak at 837.25, which basically the ensemble of mercury plus our probe, and we calculate the limit of detection. So for further mechanistic way, what we did the what we took the mercury sword and this our chlorine proton NMR, and we can see the peak shifted. So this peak shift happened because of the interaction with when the analyte is interacting. So definitely the electric environment is changing. So definitely we are getting some shift in the peak. And you can see this the spirocarbon. So this 73.17. So this is missing in after binding with the mercury. So that means when this is binding, so definitely this ring is opening. So that's why we are getting the planarity. This molecule is getting the planarity, and after getting the planarity, it is showing the fluorescence. So this is also fact that confirm that there is like this big absence means that opening of the spiro like a ring is actually open, and it is showing the fluorescence. So whatever we got in 837.278, so we theoretically also we compared that okay, our pattern is actually matching. So we put the molecular formula, whatever we are expecting with the uh, binding after binding that analog. So what we put that structure, and theoretically and even experimentally we see that all the things are matching. So that means whatever we are claiming that this is after binding is forming, so that is true. So then we check out the usability and recyclability of the analog this sensor. So what we did, we just first put the mercury there, then we put iodide, a person iodide, high between we put. So we see that again it decreased. So you can see towards 330, it's almost maybe you will change happening. So that means it is reversibly binding. So we can, so this is the like it's our insert. So which bind with the mercury 2 plus, and which is reversibly again they coming back to the sensor molecule when you have to iodide because the mercury iodide is forming, and so again it is becoming a free sensor. So you can see the color changes with after binding and after putting the iodide. So then here that we did the time result spectroscopy or TCSPC study. So here you can see the black lines basically are from there's only disease or only with the solvent. Then what we did the decay, we analyzed the decay time of the sensor and the decay time we checked with the mercury. So as from this, you can say the lifetime basically decreased. Lifetime decrease, but the quantum mean see 0.0014, 0.014 to 0.42. So quantum mean highly increased. But your our time that tau average that is lifetime basically 0.56 to 0.18. So which is obvious because now it is all not in excitation because it came to the fluorescence state to the non state. So because that opening the non-radiative the decay channel, so which is basically in the kinetics of the radiative channel and non-radiative, you can see the non-radiative channel that kinetics is 1.76 to 3.23. So which means that and but whereas so that is the reason for the getting lower tau value or the lifetime value. But if you see the radiative constant also, the constant, it is also 0.025 to 0.2.32, which is high. Because of that only we are getting the fluorescence. So so it is also another proof that okay, so this fluorescence opening only happening in presence of the that analyte that is our mercury plus. Then we tried for the cell imaging study. So before any biological application, so we need to check the. So what we did the cell viability study by MPT as a method. So you can see that 50% or IC50 if you calculate the linear fit. So when we do the IC50 study, so we found that 6.9 micromolar was the IC50 value. So till like 6.9 micromolar, so that means So one for our application purpose we use 1 micromolar concentration, so which is far lower than our IC50 value, or you can see almost in one this our 1 micromolar of concentration, almost 90% of the cells are viable. So we can say this is fairly non-toxic in nature. So we used this concentration for the cell viability, for the cell imaging study. So this is a fact study. So with the time also we checked. So this is the control intensity was like 21. So when we used for 20 minutes and 40 minutes, we see there is no much change of the intensity. So that simply tells that our cells can in 20 minutes and 40 minutes also with the time also cells are intact. So there is no much cell that happening. So now these are the imaging and these are the quantification of imaging. So we use some software that render 3D. So where the quantification of the our this imaging will be. So these are different concepts. So this is the control, the bright field image, and this is the control image. Then with the change, when we increase the concentration, so then we see the cell can fluoresce more, and it can be visible from our heat map also that with the concentration how it is changing. So we did for two type of cell. One is the HeLa cell line, and another is the SHSI5, which is a neuroblastoma cell line. So as I told that initially that our target was that that molecule we use that tryptamine, which is basically a part of a neurotransmitter. So that neurons and also we have to check, and we see okay there also we can be able to image in case of mercury. Mercury is present, then only it will put and you can check you can take the image. Uh, so now for the practical application, so these are like biological applications. So practical application what we did, we take different kinds of water samples like drinking water, then tap water and river water. So there also we added maybe spike if mercury poisoning is there. So then we check the limit of detection. So we can see 2.9 nanomolar, 2.62 nanomolar, and 3.1 nanomolar is the limit of detection. So which is fairly lower than the US EPA standard. So and you can see the color. If this is when we put in millimolar, in nanomolar concentration, so we can see the color changes and even the fluorescence changes also. So then we did the recovery study. So we used 50 nanomolar, 100 nanomolar, 300 nanomolar of mercury spike, and we see there is a recovery rate of like 96 to 98% for the drinking water. For tap water, it was like 101 to 109. This is little bit high because that water quality also depends like how it is binding and this thing. And river water also you can say still 95 to 99% recovery we can able to do. So that is it is really we can say this is water content is there in mercury. So if this sensor can detect mercury easily. So for solid state application, like if we now what we do, so we take the same normal our filter paper. So where we put the compound and then we put drop of mercury. So you can see there is like white color and this time slightly bluish color happen. Okay, so this is in bare eye and in fluorescence you can see there is very little fluorescence in probe, but in place of mercury there is high fluorescence you can see. So that means in solid state also it can recognize it. So if we can make a like a pH paper kind of strip, so it will be that also can easily will be able to detect the mercury. So these are the different water sample images, and this is the FBS protein liquid. So in FBS protein also we spike mercury and we give our compound. So you can see in fluorescence like this, like that F is the fluorescent light mercury plus our compound in FBS protein. So in protein sample also we can detect mercury. So the compound can detect in water sample, it can detect in protein, it can detect in uh, solid state. So practical application have fairly practical application, and we can do the cell imaging study also for different kind of cell lines. So somebody can say that we have developed a mercury sensor, so which basically strong orange fluorescence or deep in color forming after binding mercury, and it's having the 1:1 binding stoichiometry as per the log plot and mass spectroscopy, and it is able to it is very non-toxic and it can be able to pass through the cell wall of the cell system, like neuroblastoma cell line and cervical cell line. And it can directly interact with the intercellular mercury 2 plus, so it can be used for the biological imaging. The limit of detection was 2.1 nanomolar or 0.42 ppb, which is far lower than the US EPA tested value. And this sensor can be used for the environmental water sample of mercury sensing. So this was basically our turn on this sensor, like where the fluorescence on non-fluorescence to fluorescence thing happen. So another thing is we want this is a thymidine-based molecule for copper 2 plus, which basically turn off sensor. So how is inside? We took the array glycol in presence of the array amine. So then we can get the intermediate I, and then we use their polyethylene glycol, sulfonic acid as a catalyst. So for this we took the polyethylene glycol, and then we reacted with the the chlorosulfonic acid. Then we got this sulfonyl group, and then we place on the this cumin. Then we fuse that pyrrolofused cumin form within that code, and we took different like these three molecules actually we size with different electronic structure and different functional group, and then we checked out that thoroughly we checked the fluorescence properties. So what we did, so as I told you, first we have first and foremost thing that we have to choose the proper solvent. So from polar to non-polar, we just take like BCM, dioxane, ethanol, acetonitrile, and NFA. So we found that acetonitrile have the better fluorescence intensity, and you can see that if it's so stable, so we can see the quantum yield also is maximum in case of acetonitrile for all the cases, all the molecules, 4A, 4B, and 4C. And out of all this, 4B having maximum quantum yield of 0.404. So that's why we took 4B as a model sensor to proceed further. So what we did, we again are here also for the CFTV study. So what we did, we used several metal ions, and we see in presence of copper only, the peak which is at around 340 shifted to 380, because that's why this color is generating. So you can see in this image, so this photograph, the color is ending in presence of copper only. But in fluorescence, what is happening? All are fluorescent, but in presence of copper is not fluorescent. So we can say this is particularly specific to the copper 2 plus. So what is the titration? So it was like when we add 2 equivalent of copper slowly, we see almost 50 times, 50-fold increase actually happened. And here in B, you can see the this 340 wavelength around 340, 335 to 40. So it is keep on decreasing with addition of copper 2 plus, and peak at 380 is keep on increasing. So that means its color this is whatever forming. So it is basically forming after binding with the copper 2 plus. Then again we took the response time. So you can see different equivalent of copper 2 plus check, and everywhere we see within 1 minute time this is very fast binding. Within 1 minute of time the binding is happening. And in presence of copper we check here also you can see this lifetime also decreases like from 2.6 to 1.27, and that is because of I told earlier that because of the opening of the non-radiative channel. So this because of this, the decay time also decreases. So we did here also that same like job spot, and we see 1:1 binding, and we found that it is also 10 to the power 5 range of binding constant, and we calculate the limit of detection also. So further, what we did the same like Proton Nmr titration. So you can see this binding of NH, this NH proton, like this is, as you know that NH is having the higher affinity towards copper 2 plus. So this hydrogen, this NH is actually binding to the copper 2 plus, and then double bond O, that is also basically binding with copper 2 plus. So then you can see this NH proton basically after adding of the copper 2 plus is missing. So we can say there is a binding through this nitrogen, and we can see this carboxyl stretching frequency in the FT also. If also shifted, so that also further confirmed that these two are the main binding site to bind with the copper. Then we did the mass spectra study. So this is our compound plus copper plus perchlorate as the counter anion and hydrated, because all these inorganic complexes can form the hydrated also. So this is the basically the structure is forming after binding, which is basically showing this color and which is basically showing this non-fluorescent nature, which is quite obvious, because when it binds, so the planarity of this molecule definitely it will lose, because this free rotations all will stop, so definitely we get the less fluorescence. So here also we did the cell line using HeLa cell imaging. Here also we took the regular stuff, like we did the MPT assay and we did this imaging, and you can see in presence of only compound, this is highly fluorescent cell, but when copper is there is no fluorescence. That is the turn of fluorescence happening. Then we did the jet stacking with the different focal length. We just check, and it was find that 15 to like 18 micrometer of this range. It was the maximum we could achieve. And we then, after doing this, we took all the images in that, and we found it was very much useful. So we got the limit of detection of copper 2 plus, which is 11.3 nanomolar. So 2 ppb, which is very less than 1.3 ppm of copper, which is the USEPA threshold value maximum quantum that MCL. So you can see this is ppm, but we got in ppb, and it was like from John's plot, you can say it's 1:1 binding, and this is also turn of stressing in presence of the cancer cell line. So you will be able to do the same study also. So here we discuss about that one for the turn on sensor, one is the turn off sensor. Now aftermarket sensor. So now aftermarket sensor, if you see, so there is a this is the general aftermarket procedure for the aftermarket sensor. So what it will happen? So aftermarkets have like specific bind with the analyte. If it is like toxins or like if it is target toxin, so what will happen? So your aftermarket, when it will bind there, so definitely if it is electrochemical or if it is colorimetric, so there will be definitely change in that. So if here is the example, like if you have a graphene with this aftermark, so when it is binding with this, so then you can see this is fluorescent. If it is like carbon conductor, so it will be fluorescent. When it is bind, so there is no fluorescence. After bind, when it bind with the analyte, so definitely it will become fluorescent. So here also you can see this aftermark is binded with the ferrocene. So that is the electrotransfer can happen. But when it bind with the analyte, so definitely this finished, and we are getting the electrochemical sensor, like electrochemical signal, and you can say it is a sensing. So then the beauty we found that antibody aftermarks are small molecule, it is cost effective, and you can first and foremost you can store it very easily in room temperature. Even in room temperature you can store it, and it is having white. You can just change the aftermark structure, and definitely your specificity will change. So as per your analyte, so you can make your aftermark, and you can have your aftermark, and you can get your sensing. So gold nanoparticle based after sensing, this paper, one paper, so you can see. So when it is binding with this uh, like our aftermark, so there was like fairly it was like stable. But when it bind with when this gold nanoparticle was stable, but when we give that mercury, so it immediately binds with the your aftermarks, and it is free, and we start agglomerating, and you can see the color changes or the pixel in the individual spectroscopy. So which is basically the gold nanoparticle based colorimetric is mercury fluorescence. So this is mesoporous material based like red sensing. This what we did in University of Leeds. So what we did in mesoporous like silica, we just make it functionalize it FETS and then bind with the FIBC, fluorescent isocyanide. So which is basically non-fluorescent in nature. So when we put the lead to plus, so immediately it bind, and you can see in confocal, you can see the this fluorescence. So these are all are like these channels like SBA15 is a porous material, all the pores equals porous. So when we add quencher there, so we can see this quencher. So for this specifically what we did lead and cadmium. So when we add increase, we increase the addition of lead, so we can see 100 nanogram per ml having huge fluorescence. But when we add here the cadmium also, but cadmium intensity was basically lesser than lead 2 plus. And in presence of cadmium and lead also we checked and we got almost similar kind of pattern in the lead. So that means it's specific to the lead, we can say. Now, why we are doing all this? So basically, our target is for a essentially development of a receptor or a molecule which can basically sense the heavy metal. So then we have to immobilize this receptor into to fabricate the sensor. So then, if we add a heavy metal, either color will develop or some electrochemical electron like this generation will happen, or we can say that you can change in the resistivity or might be the your voltage or current it will happen. So after that, what we can do, we can make a handheld like device system, basically some uh, app-based system. So which can like if you are going to the field and you are having water, so you just add your sensor, immediately color generated, the scan using smartphone. So definitely you will get because there will be already calibrated curve will be there. So it is okay. This is that this much of ppm or this much of ppb of your analyte is there. Then automatically you will be like okay, I should drink it or I should not drink it or I should use it or not. So this is basically the main concept in which basically we are working now with my collaborators. So now we are basically working for development of some arsenal-based sensory device, basically app-based device. Uh, so now I speak about my little like 5 minutes about my institute. So this is basically my institute, Satyabama Institute of Science and Technology, which basically Dhempe University have NIRF ranking 40, and we are having total student strength of near about 18,000 students. So several streams are the like science, commerce, arts, and medical, even engineering. And here is our research center. This is the international research center where I am basically working. And so these are the facilities, and these are the like for fabrication facilities. So these are the PVD, PVD, and CVD machine. So these are basically people are working for this thin film deposition and carbon nanotechnology research and all these people are doing. So basically, our department we have near about 25 odd scientists and a total strength with some scientific assistant and scholar. We are having near about a group of 64 people now working, and we are trying to do some research there. And these are the characterization facilities. So we are having the SID, efficient, and these are Raman Specter facility we are having, and this is the process which to have a cell imaging study basically is to do using this. And so within I think 1 or 2 months we will get to new transmitting instrument study, and another one more FACM and one more XRD is coming, and we are now going to inaugurate that 3D printing laboratory. So these are the Raman Specter and fluorescence spectrophotometer where that fluorescence research I am doing basically now. So these are the metrographic equipment. So these are cutting machine, polishing machine. So these are there. And these are the biochemical facilities. So basically, our department is composed of different like science for different fields. Like we are having chemistry, physics, microbiologist, even biotechnologist, and some chemical engineering background. So it's a like combination of a group which having the different expertise and we are like trying to do or something. I can say that last year we for our center only we published around 84 articles and we got some 14 odd patents. So we are trying to do something, and if anybody interested to use the facilities or for internship or for training program, then you're always welcome. So you can contact me. So we are frequently are organizing some programs for particularly for the students, like to hands-on training program for different topics. So if anybody interested, they can easily come. And for the faculties, I can say if for research purpose, if you want to collaborate, you are always welcome, sir. So we definitely try to do our best and we try to help. So now for activation, I just want to thank my institute, Southern Institute of Science and Technology, the organizing committee for inviting me. To my PhD supervisor, Professor Nalina Ghosh, my postdoctoral mentor, Professor Ramesh Pavani, Professor Paul Milner from University of Leeds was my collaborator. Now I did this research in like University of Calcutta and Department of Chemistry Goa campus. So basically I did my PhD from Goa only. So all my collaborators and my lab colleagues and the funding agencies like who are helping me for my doing my research like UGC, UGCD, CSR, DRDO, CSR. So I'm really thankful to them for providing me the funds for doing my research. So thank you very much.
Thank you, sir, for highlighting the importance of small molecules as sensors for heavy metal detection. I request participants to post their questions, if any, in the chat box. Participants can also unmute their mic and ask the questions directly. Yes, there is one question by
Yes.
Dr. Chandan Naik in the
Yes.
chat
Yes.
box.
Yeah.
He is asking why the rhodamine-based sensor is only specific for the detection of mercury ions.
Okay, ma'am. Thank you, Dr. Naik, for your question. Actually, rhodamine-based sensor, particularly what we prepared here. So, if you see the structure, so I just go to the structure. Yeah. So, this is it visible, ma'am? This right?
Yes, sir.
Yes, sir, visible.
Yeah. So, if you see the structure, so when we got this double bond O moiety, which keep coming, so this moiety was basically specific to the trivalent patterns. Okay, so when we change it to double bond S, when we introduce the soft center, so that time only it binds with the mercury. Okay, so it's not like the rhodamine base is only what when it is having double bond S, this structure, so then it is particularly specific to the mercury because for any sensor work, it should be in your mind that definitely it should be specific to a single analyte. So yes, there is this. So reports are there for the multiple analytes, but if more number of analytes it can detect, so specificity will be less. So definitely the novelty of your this sensor it will basically reduced. So if it is like you have to tune like such a way, so which will be like specifically bind to the particularly single analyte. So when we did this, that time also we didn't know that okay, it will be like, but we know it will be like particularly binding to the stop center definitely because double bond S is there. So, but we checked, but we got the monthly it is having, but we checked with lead and all. Okay, but as you know that depending upon the electronic structure and the configuration, so it depends like which kind of metal. And another thing is that your S in this cage, whatever is that radius, so it should basically fit with your metal and ionic radius. So if it is like if instead of 2 CH2, if it is like 4 CH2 or 3 CH2 chain, so definitely radius will be more, so it may not be suitable for mercury. Okay, so depending upon all these factors, we can say this is like specific to mercury.
So next question is by Madam Varsha Virjinkar.
Asking any sensor you
She
can
is asking
suggest
any
for
sensor you can
cadmium
suggest,
ions.
sir, for cadmium ions.
Yeah, yes, cadmium ion definitely we can like this now also I am working with cadmium ion. So like there are several like chemical moieties basically can use for this. But for cadmium and all, the problem is that this binding with the even sulfur also it will be like not so like easy we can say. It is very direct concentration with some. So for cadmium sensor, I will suggest to make like electrochemical sensor. Okay. And another thing like now I am working on the carbon dot space sensor. Carbon dots provide fluorescence sensor. If you modify this carbon dot structure, okay, and you can get a good like cadmium because this if it can like change to cadmium, it can form the cadmium sulfide kind of thing. So then definitely I think it will be used for the cadmium. But for this cadmium, what I feel this going for the electrochemical sense will be easy to make. Then that also like basically we are working here now. So some you can see some graphene based material or some biometric allergen material. It's like sulfur group like things that we can really explore for the cadmium.
Are there any more questions from the participants? Yes. Our next question is from Dinesh Nadir Mitla. Is there any effect of counter ion on detection of Ag2 plus ion?
Yeah, counter ion means we interfering ion we check. Okay, but counter ion basically we check for chloride and perchlorate because if you see that I give the NMR practices in perchlorate. But there is no counter anion, there was not much difference. Okay. But when we check with the interfering metal ions, so there is found that all interfering metal ion in presence of mercury also, when you put the all interfering metal ion plus our sensor, so there was no signal basically. But when immediately we put the mercury, so within 3 to 4 minutes time we got the color. So that means it is specific to Ag2 plus. But for counter anion, we didn't find any like we checked with perchlorate, we checked with nitrate, and we checked with chloride. So there was not much difference.
I think there are no more questions, sir.
Okay.
Highlighting the importance of small molecules as sensors.
Thank you, sir, for highlighting the importance of action. So, thank you once again for accepting our invitation. Now I request Mr. Shashank Maldar, Assistant Professor, Chemistry Department, to introduce a second speaker of today's webinar, Dr. Salman Khan.
Hello. Actually I am having one class, so can we leave now?
Yes, sir, no problem.
Okay. Thank you. Thank you.
You can leave.
Good morning to one and all. It's indeed an honor to have in our midst today Dr. Salman Khan as a research person who is an alumnus of our institute. Dr. Salman is currently working as a postdoctoral fellow at Department of Chemistry, Nanoscience, Biochiral Lab at Eva Women's University, South Korea. He has completed his BSc in Chemistry from our Dhempe College of Arts and Science. He did his post-graduation studies in Organic Chemistry from Goa University. Dr. Salman has qualified CSIR UGC NET in December 2012 with All India rank 81. Then he moved to IIT Bombay for doing his doctoral studies. In 2021, he was awarded PhD degree from Indian Institute of Technology, Bombay. Dr. Salman has worked as a research associate at Syngenta Biosciences and also as a postdoctoral associate at IIT Bombay. He has 5 high-impact publications to his credit. His research interests include CH activation on challenging scaffolds, then cascade reactions and heterogeneous catalysis. With this brief introduction, we welcome you, sir, to this national webinar, and I request you to kindly start with your lecture on CH functionalization.
Thank you, Shashank. Am I audible?
Yes.
Okay, so should I start?
Yes, please start.
Okay. So I will share the screen.
Come to the office. Just wait.
The screen is visible?
Yes, it's visible, yeah.
Okay. So I'll start. Good morning, everyone. First of all, I would like to thank the Department of Chemistry, Dhempe College of Arts and Science for organizing this seminar and giving me the opportunity to present my research work I carried out during my PhD at IIT Bombay. Since majority of the students are undergraduate and graduate students, I would like to make the topic as simple as possible. Since my aim today is to give the students a just gist of the research, how research is carried out, and maybe encourage some of the students to take up research. So let us start the topic. The title of the presentation is Bronsted acid catalyzed CH functionalization of aryl sulfoxides via thiaclazine rearrangement. Sulfur compounds are highly valued molecules as they find their presence in a vast number of natural products as well as pharmaceutical drugs. Their importance can be realized by the fact that recent study revealed that almost 20% of the pharmaceutical
Hello, sir.
Yeah.
Sorry to interrupt you. Actually, we
Yes.
can see the last slide, the thank you slide. Please go to the first slide.
I have the first slide on my screen actually. Okay,
yeah, now we can see the first slide. Yeah.
Now is it okay?
Yes.
Okay, fine.
Please make it.
Dr. Salman, please change the slides and see. Many times it does not. It is not seen then.
Okay, ma'am.
This is just change it. Yeah.
Is it working?
Change and see.
Actually, I'm changing. Can you see?
No. Only the first slide is seen.
First slide is there. Oh, okay. Let me try to use it. Save. I'll try to open the slides again. Now, ma'am?
Presentation itself is not seen.
Sir, can you please switch on to the full screen mode? Present the entire screen.
Yeah. Is it fine now?
Okay, it is not the full screen mode.
Oh,
Make it full screen.
I can see the full screen actually.
Okay.
But the slides are changing at least?
No.
Oh.
No, only one slide is seen.
Oh, wait a minute.
Then change it.
Yeah, actually I'm changing.
Okay, slides are changing. But if you have given animation, it will not be seen.
Yeah, actually. So with the the slideshow mode, it's not showing, right?
Yeah, because it is not coming as a slideshow.
Okay. So animations. I'll just one more time. I'll try to see.
Go to slideshow and then you have an option there. Okay, and then come to the full screen, because here full screen, I think you have gone on the slideshow upper menu bar. Come to the lower menu bar and make the slide this thing.
I'm using the lower menu bar. I'll try to do it with the upper one. Let's see.
Okay, try with the upper one.
Is it changing now?
No.
No, it's not changing. So can you go to that share screen mode and then present the entire screen?
Okay. Stop sharing. Okay. Is it okay now?
Yeah, now it's visible. Yeah,
Okay,
slides are
okay,
properly changing. Yeah, you can start.
okay, fine. Okay, so should I start from the beginning?
Yes.
Okay, so the topic for the presentation is Bronsted acid catalyzed CS functionalization of aryl sulfoxides via thiaclazine rearrangement. As we all know, sulfur compounds find their presence in majority of the natural products as well as pharmaceutical drugs. Their importance can be realized by the fact that recent study has revealed that almost 20% of the pharmaceutical drugs sold in the US in 2012 had sulfur present in one or the other form. So some of the commercially available drugs I have shown here. So these are the sulfur containing drugs which contain the thioether moieties, then the sulfoxides, the sulfones, and sulfonamide, to name a few of the classes of the sulfur containing drugs. And they have the bioactivities vary from antifungal, anti-malarial, antibacterial, and anti-inflammatory. This element is special because of its ability to exhibit oxidation states ranging from -2 to +6 in these molecules. To, to show the importance of these molecules in the organic synthesis, I have shown some of the organic reactions, such as the first one here, the Korechkovsky reaction, wherein the reaction involves the use of sulfur ylides in the form of sulfonium ylide as well as sulfoxonium ylide, which can be prepared from using dimethyl sulfide or dimethyl sulfoxide by treatment with methyl iodide, and then using a strong base such as sodium hydride to give the ylide, which can react with ketones or imines as well as the alpha beta unsaturated enones to give epoxides, aziridines, as well as cyclopropane compound. The next one is the use of dimethyl sulfoxide as an oxidizing in the dimethyl sulfoxide in combination with oxalyl chloride is able to oxidize the primary and secondary alcohols to the corresponding carbonyl compounds. The drawback of this reaction is this reaction has to be carried out at temperatures below -25 degrees, as these the intermediate which is formed is very explosive. So very relatively milder reaction wherein dimethyl sulfide is used is the Corey-Kim oxidation, where dimethyl sulfide in combination with N-chlorosuccinimide is able to do the same oxidation process. And in addition to this, a variety of name reactions are known in the literature. One such reaction is the Nmr rearrangement, which is the reaction of alkyl sulfides. When they are treated with acetic anhydride, it rearranges itself to give the alpha acyloxy sulfide compounds via this intermediate. So recently, scientists came up with an idea that instead of acetate acting as a nucleophile, they've used a better nucleophile which can directly attack onto the sulfur cation and knock off the acetate group to give a intermediate which has all the prerequisite for the Claisen type of rearrangement, and we can get functionalized aryl derivatives. So this intermediate can be obtained in two ways. First, by the above shown method, where we take anhydrides and directly treat it with the sulfoxide, and the nucleophile attacks onto the sulfur and the acetate leaves. But this is a very this has a drawback, which is the stoichiometric amount of metal waste is generated. More recently, a new method has been developed wherein more elegantly only catalytic amount of Bronsted acid can do the same job. Herein, instead of activating the sulfoxide, the pi electron partner is activated by wherein the pi electron cloud reacts with the Bronsted acid to generate a cation, which is trapped by the sulfoxide, and then the stage is set for the thiaclazine rearrangement. So let us see. So let us see some of the literature review. In the first paper, what they did is they activated the sulfoxide with trifluoroacetic anhydride, and then they used phenol as the nucleophile, and this is the precursor for the thiaclazine rearrangement intermediate, which the rearrangement takes from. Next one, instead of using the phenol, the scientists came up with the methodology where a nitrile is used as the nucleophile, and so they can easily functionalize the arene ring with acetonitrile moiety. And this is a uranium type of an intermediate which is formed. Next, the newer methodology where acid was able to activate the alkynyl amides as well as alkynyl sulfides to generate the carbocation, which was again the sulfoxide attacks and to give the product. So motivation of the study was that since in our lab we use most of the allenes, we work extensively on the use of allenes for the CH activation and CH functionalization of the allenes. Here in the example, quinoline N oxide on reaction with alenil acetate in presence of cobalt catalyst was able to give the CH dianylation of the product. So keeping in this in mind, since most of the majority of the reactions involved alkynes as the pi coupling partner, we thought why not we can use the allenes as the coupling partner. So our objective was to treat the alenyl alcohols with acid catalyst to generate the protonated species. The protonated species then the sulfoxide will attack to generate, and the subsequent loss of water molecule would generate the vinyl sulfonium cation, which can easily rearrange to give the vinyl thiaclazine rearranged type of product. So briefly we'll see about the difference between the allenes and the alkynes. So both in alkynes, both the carbon atoms involved are sp hybridized. As a result, what happens is the alkynes are linear and with two double bonds, with two pi bonds. What happens is the alkyne sigma bond is totally forms like is shielded by the pi bond like a cylinder. But in case of allenes, what happens is, just a moment please. Yeah. So what happens is when in case of allenes, the central carbon is the sp hybridized carbon, and both the terminal both these terminal olefins are sp2 hybridized. So which forms like two distinct planes. Here one plane and the other plane which is orthogonal to the other plane, which, because as a result when disubstituted allenes are used, they can be chiral, as they have a chiral axis which passes to these three carbon atoms. So keeping this in mind, we wanted to use alenil alcohols in the thiaclazine rearrangement. So coming to the optimization, we reacted three equivalents of diphenyl sulfoxide with alenil alcohol in presence of triflic acid, 20 mole % of triflic acid in DCM solvent at 50 degrees Celsius, and we got about 31% yield of the product in 2 hours. So next we thought maybe that water which is generated is interfering with the reaction. So instead of alenil alcohol, we used alenil acetate for the same reaction. We got a slight increase in the product yield of the product, but it took about 16 hours for the reaction to get completed. So in order to take care of the desiccant, in order to take care of the water molecule which is generated, we used desiccants such as calcium chloride, molecular sieves, as well as magnesium sulfate. And if we found out that within 4 hours, in case of magnesium sulfate, we got about 53% of yield of the product. So next, what we did is, instead of DCM solvent, we changed the solvent from DCM to nitromethane and got about 68% yield of the product. Then next, we turned attention towards optimizing the Bronsted acid source, and we screened different Bronsted acids such as paratoluene sulfonic acid, methane sulfonic acid, benzene sulfonic acid, trichloroacetic acid, and trifluoroacetic acid. And we found out that trichloroacetic acid gave about 69% yield of the product, although it took about 24 hours for the reaction to get completed. So when the same reaction was carried out with 2 equivalents of trichloroacetic acid, instead of the usual catalytic amount, 71% yield of the product was obtained. But it took about 8 hours to get completed. So instead of going for the trichloroacetic acid, we chose a trifluoromethane sulfonic acid as the catalyst. And when on increasing the temperature from 60 to 80 and 90 degrees, we found that 80 degree was the optimal temperature for the reaction. Further trying to decrease the amount of sulfoxide which is used, on using 3 equivalents as well as on using 1.5 equivalents, the yield considerably decreased. So we went ahead with this optimized condition. And once having the optimized condition in hand, we went for the screening of the substrate. So first, allynyl alcohols we screened, various allynyl alcohols, monosubstituted secondary allynyl alcohols with alkyl chains as well as phenyl rings gave good yields of the product. Monosubstituted tertiary alcohols such as these ones also gave excellent yield of the product. Alcohols bearing cyclohexyl moieties gave good yields of the compound, but there was a mixture of 1:4 ratio of alpha beta and beta gamma unsaturated product. This can be attributed to the acid catalyzed tautomerization to the more stable endocyclic double bond. Next, the disubstituted allynyl alcohol such as these also gave good yields of the compound. Next, we turned our attention to the scope of the sulfoxide. Diaryl and aryl alkyl sulfoxides gave excellent yields of the product. The sulfoxide bearing electron withdrawing as well as electron donating substituents at the beta and the gamma position, alpha and beta position of the alkyl chain also gave decent yields of the product. The sulfoxides having activated as well as deactivating groups on the aryl ring also gave quite decent yields of the product. The sulfoxides bearing heteroatoms such as pyridine as well as dibenzothiophenone also underwent smoothly under the reaction conditions to give the desired product. Next, we tried to increase the applicability of the reaction by carrying out a gram scale synthesis of the reaction of the product, wherein 1 gram as well as 1.5 gram of the allynyl alcohol was reacted smoothly under the device methodology to give 1.06 and 1.85 grams of the desired product. Next, the mixture 1:4 mixture which was obtained from this allynyl alcohol, we subjected it to the catalytic hydrogenation, and both the isomers gave the same product, same saturated product. Next, the sulfide which was obtained from the above reactions, the diphenyl variant as well as the phenyl methyl variant, we oxidized it with MCPBA to give the corresponding sulfoxide derivative which we have used for the sequential functionalization. So coming to the sequential base functionalization, the monoarylated sulfoxide when treated with under same condition with a different alcohol, it has two probabilities that it can undergo the bis functionalization at the same aromatic ring as well as the other aromatic ring. So we have seen that although the yields of the reaction are very low, but it preferentially goes on to the second aromatic ring, probably due to the deactivation caused by the ketone moiety. Next, the here actually there is no other choice for the reaction to take place. So the homo base functionalization takes place with about 52% yield of the product. Next, what we did is instead of the oxidizing the same sulfide to sulfoxide, we took bis sulfoxide, and under the standard condition when allynyl alcohol is used as the limiting reagent, we got about 68% yield of the um, monofunctionalized product. Whereas when the sulfoxide was used as the limiting reagent, we were able to get the bisfunctionalized product in about 56% yield. Next, what we did is, since the sulfoxide as well as allynyl alcohols both are chiral, we thought of using this information for generating chiral molecules. That is, we prepared the sulfoxides with enantiomeric ratios up to 95 to 5, and we were able to get the chirality transfer from the sulfur stereo center to the carbon stereo center with enantiomeric ratios of up to 90 to 10%. And here with the substituents, we can see that as the substituents tend to be bulky, the enantiomeric the chirality transfer is much better. And with the substituents like N-propyl and cyclohexyl, the enantiomeric ratios are very tend to the product tend to racemize. So then next, what we did was we prepared a chiral aniline, that is 98.5 is to 1.5, and we carried out the reaction to check the chirality, to see whether the chiral information from the alene is being able to transfer to the to the product using a racemic sulfoxide. So in that case, we found that only a racemic the product was formed. Next, since we use acid in the reaction and we have the ketone here present, so maybe we thought the slight deterioration in the an enantiomeric ratio of the compound was attributed to maybe possible because of the ketoenol tautomerism which can occur. So we took the sulfide bearing enantiomeric ratios of up to 90 is to 10 and subjected it for the same reaction for 1 hour, and we found out that there was no deterioration in the enantiomeric ratio of the product. So just for the sake, the enantiomeric ratio of the enantiomeric ratio of the product was determined by chiral HPLC, wherein both the R and the S enantiomers were separated by using a chiral stationary phase, which interacts with the chiral product, and both the enantiomers are able to interact differently with the chiral stationary phase, generating a diastereomeric interaction with the stationary phase, and that's why they can separate. And after separating, we have run the same chiral sample, and we found out that the enantiomeric ratio of the product was about 90.5 is to 9.5. Next, the mechanistic studies. What we did was we prepared a diaryl sulfoxide, wherein one of the aryl ring was substituted by D5 compound, and then we carried out the same reaction under same condition, and we found that the ratio of the product wherein the H is functionalized to the product where D is functionalized, the ratio is called pH by PD, product distribution ratio, was about 1.5. This indicates that when product distribution ratio is above 2, it indicates that the CH bond breaking step is involved in the rate determining step of the reaction. So as we all know from the mechanism, it was fairly obvious that CH bond breaking was not the rate determining step of the reaction. So coming to the mechanism, acid on interaction with the allynyl alcohol generates a protonated species. This protonated species then the sulfoxide attacks onto the carbon atom and subsequently knocks off the water molecule to generate the butadienyl sulfonium cation intermediate, which on thiaclazine rearrangement and subsequent loss of a proton regenerates the acid catalyst and gives the product. So in conclusion, we have developed a Bronsted acid catalyzed functionalization of aryl sulfoxides by using thiaclazine rearrangement as the methodology, and we have about 54 examples with mild conditions and yields up to 89%. We were successfully able to demonstrate the chirality transfer from the sulfur stereocenter to the carbon stereocenter, the gram scale synthesis, sequential functionalizations, and mechanistic investigations are the highlight of this study. So I would like to thank the Department of Chemistry, Dhempe College of Arts and Science, organizing committee of the seminar for giving me this opportunity to present my work. My supervisor, Professor Chandra Mr. Volla, Department of Chemistry, IIT Bombay, UGC New Delhi, and IRCC for funding. And this was my research group uh, during my stay at IIT Bombay. Thank you very much.
I thank Dr. Salman Khan for sharing his research outcomes with us, which will surely motivate the young minds. Now, I request all the participants to kindly post their questions in the chat box, or you can directly unmute your mic and you all can ask the questions directly to our speaker. So, one question is posted by Dr. Sonia Pasekar. So, the question is did you try any green acid, such as acetic acid, for this reaction?
Actually, we have not tried because for this reaction, a strong acid is required actually. So maybe acetic acid, we have not gone to that level because trichloroacetic acid, if I'm not wrong, is close to zero, I guess. Because triflic acid, the pKa of triflic acid is around minus 14. So we require a strong acid. Acetic acid might not work, but we have not tried actually. Trichloroacetic acid as well as trifluoroacetic acid we have tried, but they generally take longer reaction times.
Okay. Any more questions from the audience? If there are no questions from the audience, Dr. Salman, I would like to ask you a few questions. Can you go to slide number 7?
7.
Yes.
Okay.
Next slide, sir. Next slide.
Okay, here.
Yeah. So if you see the yield of this reaction, no, it's no, it's like around 70, or it starts from 40%, right? 40
Yes.
to 70%. Yeah.
Yeah.
So you're not getting a very high yield, like around 90%. So what might be the reason? Like you are getting your startings back, or is there any other
No, no,
reaction
no.
with the starting or alien which you are using?
Actually, the thing is, allenes are itself, they are very reactive. When you are
Reactive.
subjecting them to reaction with acid,
Yeah.
what the side product which we obtained was instead of this I think the the new bond which is formed. Can you see the screen?
Yes.
Yeah.
Can you
So
just make it to full screen?
yeah. Just can you see it?
Yeah.
Okay. So actually, this bond is not there. So instead of that, instead of sulfur attacking, the water itself attacks, and you get an enol which tautomerizes to the ketone. So that
Okay. So
side
yeah.
product was there.
Yeah. So you are getting one side product. Okay. And
Yeah.
in one slide you have mentioned about the chiral separation, no? The enantiomer ratio.
Here or the next one?
Next one.
Okay. Yeah.
Yeah, I just had one query about this. You are using these type of compounds, right? So chiral column you have used, right? So which
Yes. Yes.
chiral column you have used over here?
I have used for this particular example. I have used ODH column, but frankly
Okay.
speaking, I don't know what is the chiral material, because there are, I think, if not thousands, at least hundreds of chiral columns available.
Yes.
Yeah.
But you have
So
used chiral peg OD.
ODH. Yeah. ODH.
Okay. Yeah. Uh, yes. Thank you, Dr. Salman, for accepting the invitation and for delivering a very informative lecture on CH functionalization. So thank you once again. Over to you, Sonia ma'am.
Participants, please note that we are going to post the feedback link now in the chat box. You will get the certificate via email. Please fill the feedback form. Now I request Head of the Chemistry Department, Mrs. Varsha Virjinkar, to propose a vote of thanks.
On behalf of Dhempe College of Arts and Science, I take this opportunity to profusely thank our two resource persons, Dr. Subinjit Hazra and our ex-student, Dr. Salman Khan, for sharing their knowledge and enlightening us with their respective topics on heavy metal detection sensors and CH functionalization. On this occasion, I thank the management of Dhempe College, Administrator Sri Rajesh Batikar, and Principal Professor Vrinda Borkar for their support and cooperation in organizing this webinar. My heartfelt thanks to all the participants of this webinar. Also, thanks to all the staff of the chemistry department, teaching and administrative staff who have worked efficiently to organize this webinar. Special thanks to Dr. Chandan Naik, organizing secretary of the webinar, and key members Dr. Sonia Parsikar and Mr. Sashank Malda. Thank you all and have a nice day. Please fill the feedback form so that certificates will be available to you on email. Thank you all.
So Salman, after the end of this one, I really appreciate you for your presentation as well as the work that you are doing. So we are proud that you are our alumnus of this college.
Thank you, ma'am.
Participants may leave now.